Hello, I'm Mike McCulloch. Today I'd like to talk to you about Jupiter mass binary objects, or JuMBOs, which are a very interesting phenomenon which were recently seen by the James Webb Space Telescope. So as you may know by now, quantized inertia implies that there is a minimum acceleration in nature that applies to everything. So this can be summarized by the equation gm of r squared, which is the gravitational acceleration, must be greater than 2c squared over theta, where c is the speed of light and theta is cosmic diameter. So this must be in quantized inertia because the inertial mass of an object is caused by unruh radiation, and as the acceleration goes down, the unruh waves get longer, and at a certain point the unruh waves can't fit within the cosmos, so they're in principle unobservable, and so they can't exist. So therefore every object must have an acceleration above this value. So in 2023, Pearson and McCaughrean published a paper and noting that they'd seen what they called JuMBOs, so Jupiter mass binary objects. So these are either planets similar to Jupiter or very small red dwarfs that have paired up, and they're in a trapezium cluster in Orion, and there were about 42 of them, all paired up as binaries. And immediately on reading that paper, I thought, I bet their acceleration does not go below the QI minimum. So I collected the data on them and found that yes, indeed that is the case. So that's shown in this plot here. So this plot shows the various data from the binary objects. So on the x-axis of this diagram, you can see the separation between the pairs, between each pair, and on the y-axis you can see the mutual acceleration of them. So as you might expect, if the separation is low, if they're close together, the acceleration will be larger. So the dots are higher up on the left hand side of this plot, so those are spinning around each other quite fast. But as the separation increases, so as these become wide binaries, the acceleration decreases, and you can see that in the plot. I've also shown on the plot with the red line the QI quantized inertia predicted minimum acceleration. So of course what I was hoping for was that all these would level off and not go below the red line, and indeed they don't. So they show quite clearly that they level off, and although two of them strictly go below the red line itself has some uncertainty, so they're still consistent with the red line. But that's not the whole story. So this tends to support quantized inertia in that their mutual acceleration doesn't just decrease linearly, it seems to level off around this predicted minimum acceleration. But that's not the whole story, because what quantized inertia predicts is that for objects with a very low mutual acceleration, their inertial mass should be less than we expect. So the orbital speed, which is usually v is root gm over r, that will be slightly changed to this expression. And that means that for very low acceleration, so for these wide binary objects, the orbital speed should be slightly greater than we expect, which will boost the acceleration above the line. So that's shown here. So you can see that all these dots, the blue ones, I should say the blue ones are the new data, are above the line. But this is not all, because this makes a prediction. It enables QI to make a prediction. And the prediction is shown here, in that as the separation becomes larger and larger, the the extra speed beyond what Newton would predict will increase until it gets up to a peak of about 70 meters per second. So this is interesting because it could be searched for. This is a prediction that could be looked at and verified by HARPS, which is a telescope. And so this makes a nice prediction. So I published a paper on this in last year, well, last Christmas actually. So and that's shown here. But this is further great evidence for quantized inertia, because the behavior of these wide binaries is exactly the same as the behavior of stars and galaxies on a much larger scale. Also the same as the behavior of wide binary stars, but of course on a much smaller scale. And this is on an incredibly small scale. These are just planets orbiting around each other. So this implies that the same physics applies at different scales, but dark matter can't do that, because in order to work in galaxies, it has to stay spread out. And so you can't pack it into wide binaries, and you certainly can't pack it into wide binary planets either. So this is great evidence for quantized inertia. Okay, so I hope you've enjoyed today's short, and I look forward to speaking to you next time. Goodbye.